Right, let's talk a little bit about three-term controllers. KP means that my controller does something proportional to the error. Ki upon s means that my controller is doing something that depends on the integral of the error. In other words, the longer it lasts, the more it's going to do about it. And KDS, KD proportionality, to do with how fast my error is changing. Sometimes it helps to contextualize that sort of stuff. Okay, three-term controller. If you're driving a motor car and you're approaching a set of traffic lights which have just turned red, and your objective is to stop at that white line by the traffic lights exactly. Okay. So what you've got is a position control problem. You want to be at that white line. Controls you've got available to you typically is the accelerator and the brake in the motor car. So if I'm going to try and stop at a particular spot, what information am I going to use to decide what to do? And I'm going to suggest to you that one of the key pieces of information is how far away it is. Yeah. If that white line is 2.5 kilometers away, I'm probably not going to do very much. Yeah? If it's 2.5 meters away, I am going to do something because I need to stop. That's KP, where the controller takes an action that is dependent on the actual value of the position error. Okay, does that make sense? Can you see the connections? How far away it is, that's the measure of the error. We determine what to do. Let me do the derivative first. If this is a position control, and I'm looking at the error between where I am and where I want to be, what does this term, what happens when I differentiate that? What am I talking about in my car example? If I differentiate position, what do I get? Velocity. So this one is all to do about how fast I'm going. So if you're driving your car and you see there's a red light, I want to stop on that white line, do you think it matters what the best thing to do to the controls are? Do you think that how fast you're going is relevant information? Because if you're just trickling along the road at 10 kph, you're probably going to plan your braking for that white line stop differently to if you're barreling down there at 100 kph. Okay. So in order to get to that position sensibly, you also need information about velocity. What do you think this one does? The integral term. So I've got two terms, one of which is to do with how far away my white line is, and that determines how hard I'm going to brake. The other one of which is how fast am I going, and that's going to help determine how hard I'm going to brake. What do you think that integral term does? What if I suggested to you that I've used those other two terms and I haven't quite got it right, and I've ended up stopping 2 meters before the white line? It's better than 2 meters after it, I guess, but I'm still not right, is it? I've stopped 2 meters before that white line, whereas thinking that I'm some sort of hotshot driver, I thought I was going to stop absolutely on the line. So I've got an error. What's this term going to do? What happens if I integrate that error? Let's say it's 2 meters. It's a constant because you've come to rest, and at that time you've got zero velocity and your error signal is still 2 meters. What do you get when you integrate a constant? I don't know.
1 is rest plus c.
Don't want to talk about S's at the minute. Let's live in the time domain. If I've got a constant signal, y equals 2, and the other axis is time, and I integrate 2 with respect to time, what do I get? Somebody said it, I think. 2t. Yeah, if you integrate 2 with respect to time, you get 2t plus the constant of integration, which in this case happens to be 0, but the 2t is what I'm after. So the longer you still have that error, the larger that's going to get, because it's 2t's, isn't it? I'm drawing this from my perspective. For you, the graph goes that way. Okay. So if I leave it for long enough, the output from this term, ki upon s, gets bigger and bigger and bigger. So if I'm still 2 meters away from that line, I could arrange that term, so if still 2 meters away, do more, and it can help reduce that steady state error down to nothing. Okay, because the longer the error persists, the way that integration works, the longer the error persists, the more that controller is going to try and do about it. Okay, so there is some sense to these 3 terms. Kp, simple, straightforward. How wrong am I? The derivative term, how fast am I moving towards my goal? And the integral term, how long has it been? Am I still not there yet? Okay, so those 3 terms together will allow us to control our traffic light stop very effectively and hopefully very precisely, which is just as well, because people are trying to let cars do it by themselves these days. Okay, so that's the principle behind. That's the principle behind our simple controllers that we put into these closed loop systems. Okay. There are many other ways of doing it. We're just going to look at these because they're quite straightforward. There are very many other ways to try and modify the behavior. We can adjust system transfer functions for many different systems.